Today we are going to solve a problem that is generally asked in machine learning interviews, machine learning system design interviews, that is similar listing on vacation rental platforms. To start with, first I would like to tell you like what we are going to discuss throughout the video, and then I'll be deep diving into the topic. So to start with, we will start with the objective. Then we will jump into input and output of the system. Third, we will be jumping into the data engineering part. Fourth would be the feature engineering part. Fifth would be to discuss the model development. Sixth would be to discuss the evaluation part, that how are we going to evaluate on what we are going to build today. And seventh would be the serving part, that how are we going to serve it to the end users. Okay, to start with, what is our objective? So the objective is majorly to build a system, something like Airbnb, where once a user is seeing a listing about a hotel or a particular room, and then he sees recommendations which are quite similar to that particular thing. Okay, so that is our objective, that if user is viewing some listing, that then he should be able to see similar recommendations to it, just like Airbnb. Okay, that is the final objective that we have. The second objective would be to increase the revenue of this platform. So we can just take an example of like let's take our platform named as Airbnb only. The second objective is to if we show the proper recommendations to the user or similar recommendations to the user, there are more chances that the revenue increases, because the user is more tend to click on it and book it finally. To increase the revenue will be the second objective. Okay, now the third thing, we will be assuming few of the things initially to start with. Here, whatever we build today, we are going to make sure that we don't care whether the user has logged in or whether he's logged out. We really don't care about that. So it should be the same for both. So user can be logged in or he could be logged out as well. We really don't care. We need to show him or her the same kind of recommendations. Okay, and we are assuming that we have around 5 million listings on our platform. Listings could be of rooms like 1 BHK, 2 BHK. Let's say if you're going to Bangalore and you want to stay in a 2 BHK room, so or a 3 BHK room, something like that. That kind of listings would be, that kind of data we already have. Okay, so these are the few assumptions that we are making initially. These are the first few objectives, and this is an assumption we are making. Okay, now coming to the next part, that is input and output. Okay, input. So input is, let's say you are a user and you are seeing a listing. So this is the input, the listing the user is viewing. User is currently viewing. This is our input. On the basis of that, there is some service which we are building, some service which shows similar listings to us, like let's say top 5 listings to us. So this will be the input and output of our system. Okay, moving to the next part, that is data engineering. Okay, what data do we have? Let's see. Okay, consider that initially that user has logged in. If user has logged in, then what data would we have? We have age, ID, gender, location, and preferred language. This is the data which we will have initially. uh, okay. For the user, we have this data if the user is logged in. But if he has means he hasn't logged in the platform, then we don't have any data associated to user except the location we might have. Okay, so if the user is logged in, then comes data related to listings. Okay, let's think that whenever we open such kind of platforms, what data do we have? First is that ID of that particular listing. Let's say listing ID could be L123, L165, something like that. Second could be who is the host of that means who owns that particular house, so his ID. Third could be the price, that at what rate you will get that particular listing. Okay. Fourth would be of, let's say, the type. It could be 1 BHK, 2 BHK, 3 BHK, a villa, or some other kind of stuff. Okay. Fifth could be max people allowed in that. So sixth could be amenities, like, okay, it has a Wi-Fi, it has AC in it, or it has like car parking facility. Such kind of amenities could be listed. Okay, so these are the listings. Okay, and what other thing which we can have is a user listing kind of interaction, that okay, how it will look like. So it's going to look like something like this. A particular user went to a particular listing ID. What was the interaction type? Okay, for example, the user ID 1 went to a listing ID L123 and he just clicked on it. Okay, then it could be something like user ID 223 went to a listing ID 546 and he booked that particular listing. So this kind of data we will have with us. Okay, now we need to think that how are we going to play with this data to build our model. Okay, this completes the data engineering part. Now coming to the fourth part, that is feature engineering. Now before jumping into feature engineering, I need to tell you a few things. Okay, so see that here we have two types of recommendation system. One is a traditional recommendation system, and one is a session based recommendation system. Now what does traditional recommendation do, and what does session based recommendation system do? So what happens is that traditional recommendation system will try to see the user's generic interest. So for example, if you open your YouTube, you would see videos related to sports or some news or some other political ideology that you think is correct. So these are your generic interests which the platform has caught, and accordingly it is showing videos to you. Okay, but if you see the user could be logged out as well, so we don't have the data for a particular user, and we don't have the data related to the user's past interactions with the platform. Okay, so we can't build a traditional recommendation system here. We need some other recommendation system. So then comes the second thing, that is session based recommendation system, where for a particular session we take care of that particular session's data and accordingly show him the next recommendations. Okay, so for example, let's say you opened your platform and in that particular sessions, whatever you clicked, on that particular basis I'll be showing you new data in that particular session only. This is session based recommendation system. Okay. Now here we are only taking care of users short term interest, and here we are taking care of users long term interest. Okay, so here the problem that we are solving is to build a session based recommendation system. Okay, now how are we going to build it? We will see that. We know that we can't play with the user data at all because the user is not logged in. Okay, so we need to think something else. What data we had? We had these two datas, listings and user listing interaction. Okay, we need to take care of, somehow we need to convert them into features. Okay, we will see how. Can we think of something like, let's say for a particular session, okay, let's say session ID 1, a user entered. Okay, let's say user ID is 123. He entered, he clicked on few of the listings that we were showing him. So let's say he clicked on listing ID 140, L143, L229, L228 and L227 listings that the user clicked. Okay, and then what he did, he booked some particular listing in his current session only. So let's say listing that the user booked in that session. So let's consider that he booked L224. Okay, he booked this particular data, this particular listing. So such kind of data can be useful for us, and we already have this data with us, that in user listing interaction we already have this data that what particular user went to what particular listing ID and whether he clicked it or whether he booked it. Okay, now somehow we need to explain our model so that our model understands that this is the user's behavior. He goes and clicks such listings, and then he finally books this particular listing. So don't you think that let's consider this particular listing, let's consider this, it is a number, just a number we can consider it. Let's consider this as a number, random number. Now when the user is clicking this particular thing, he is clicking this particular thing, this, so don't you think that all of them are similar to each other? That's why he is clicking such things. For example, whenever you book any hotel or any room, 1 BHK, 2 BHK, something like that, so you always tend to book see similar things. So for example, if you are viewing a hotel that is 1 BHK and it's costing you around, let's say 12k, and then you see a 2 BHK hotel but it's costing you around 13.5k, so they are quite similar to each other. So you will see, okay, they are quite similar to each other, so they should be somewhere in the common space. So this is our end goal, that these listings, all these listings which the user clicked, they should be near to each other. If for example, if this particular listing could be presented using a number, then all these numbers should be near to each other, right? So this is our end goal that we need to reach. Now the question comes that how are we going to convert these listings into numbers, and how are we going to train our model? Okay, so let's answer the first question, that how are we going to convert this particular listing into a number, okay, or into features. So what data we had with respect to listings? Let's see. We had these particular data. We had this particular data. One by one, we will see how to convert them into features. Okay. It had a ID, it had a host ID, it had a price, it had a type, and max people allowed, and amenities. Okay. For ID, what you can do? So there could be like 5 million IDs, right? So 5 million IDs is like very large number, and we can't represent like it would be bad if we start representing number with 1 2 3 4 5 6 7 8 10 like this is bad. We need something through which a model can understand that this is a ID. So we use something called as embeddings. Okay, to represent a ID, we will represent a ID using a 32 dim vector. Why a 32 dim vector? Generally, there is this rule of thumb that we use, that is min of n comma 50 comma square root of n. Okay, where n is the number of listings that we have. Okay, here the listings are like 5 million, so it would generally mean that this IDs could be presented using a 50 dim vector. Okay, 50 dimensional vector. But for ease of calculation, I am just considering that I am representing this using a 32 dim vector. If you say so that you want to represent it using 50 dim, that is also fine. But for ease of calculation, I am just using 32 dim vector right now. Similarly, host ID could be represented using a 32 dimensional vector. Okay. Then comes the price. For price, see, for price, what you can do is that you can use min-max normalization to represent into a particular, to normalize the score. So what does that mean is, for example, your platform has minimum cost for a room to book is 1,000, and max cost for booking anything is let's say 80,000, something like that. So you can min max normalize, and for let's say our current listing has a price which is of let's say 12k. Okay, so what we can do is that 12,000 minus 1,000 by 80,000 minus 1,000, whatever comes, we just put that quantity. Let's say it comes out to be 0.65, something like that. So this price comes to be 0.65, a particular single dim, one dim. Okay, then comes type. Type again could be 1 BHK, 2 BHK, 3 BHK villa, or 6 BHK, 5 BHK. Different varieties of rooms could be there. So again, what we can do is, for such kind of things, we can use a 8-dimensional vector. Okay, 8-dimensional vector. Then again, max people allowed in the room, allowed in that particular listing, or in that particular room which you are booking. You can just apply normalization and get a 1-dimensional vector, like only a single quantity would be there. Then comes amenities. Now for amenities, the simplest solution is that you again use embeddings. Because there could be a lot of amenities that a particular facility would have. So again, what you can do is you use a 8-dim vector to represent them into 8-dim vector to represent all the amenities. Okay. So this is how, like, if you now measure all of them, 32, 64, 65, 65 plus 8, 73, 74, and so basically a particular listing could be represented using a 82-dimensional vector. Okay, like just 82 numbers. It could be like minus 0.5, 0.13, 0.25, something like that, which eventually will be somehow learned by our model. That I'll tell you how the model will learn it. Okay. So every particular listing could be represented using 82 dimensions. Okay. Now comes the question that, okay, we have this data with us, that a particular, for a session ID, we have this user ID, and we have listing IDs, which are nothing but now 82 dimensional vectors. And we have this particular thing, which is something like that, what final booking did the user did. But how do we make sure that somehow our models learn this pattern? Okay, so for that we come to the next part, that is model development section. Okay, so for model development section, to start with, see, you could think of a lot of things, but the simplest thing is whenever you need to learn embeddings, go for a neural network. This is the first thing. Whenever you have embeddings, go for a neural network. Now, second question is, what kind of neural network would it be? Would it be a deep neural network, or a shallow neural network? How to take care of that? Okay. See, here we need to make sure that the recommendations that we are showing has to be shown in like the least possible time. Okay, and the listings will be done almost every other day. Okay, so we need to make sure that the model size is less. This is the first thing. So we don't go for a really deep neural network here. This is something which we can think of, that okay, we don't need to go for a deep neural network. But what is this shallow neural network and how are we going to use it? Okay, let's take an example. Now let's say that there is this user one. He clicked on these particular IDs, A, B, C, D, E, and then he booked this particular ID. Now, whenever I say that these particular listings are just embeddings, now if these are embeddings, in the embedding space, they should be near to each other, right? So it means that if I calculate the cosine similarity between them, or if I do even a dot product between them, the score should be high, right? So we can something think like, either we need to do a dot product, or either we can do a cosine similarity. We can go with anything. And in the embedding space, A, B, C, D, E, A, B, C, D, E, and F should be near to each other. Okay, so we need something which brings all of these embeddings near to each other. Okay, this boils down the problem that we somehow need to bring all these embeddings to nearby to each other. Okay, now the next thing, that if let's say we have this attitude vector, okay, and we think like, okay, if let's say the user is seeing this particular listing A, then the user if the user is clicking B, then it is a positive thing for us that the user found it similar, right? So we can add a label as 1 ahead of it, saying that if the user was seeing the listing A and then B is similar to that, so it's a positive label, right? Similarly, if user is seeing C, then he can see D as well, which is near to it. It has a label 1 associated to it. If the user is seeing D, then and we can have a random negative sample right now, let's say G. A label could be added 0, that hey, for if the user is seeing the listing as D, we are making sure that the D does not show in the recommendation, because G is a random listing which is nowhere in the click listings, right? So the final data set that we will use to train our model is that something like, for a particular listing A, let's say he clicked on the listing B, so that is a positive sample, that means 1 as the label. For a listing C, D is the one which comes in our recommendation, so D is the one which the user clicks the next listing, so again it is a positive label. So it means that what kind of problem it becomes? It becomes a classification based task, that for a particular, whenever a user is seeing a listing, let's say the user is seeing A. Okay, now we need to show him listings for which the score would be closer to 1, right? This is something which we need to solve. And if it becomes a classification problem, there will be probabilities associated with it. But how will the probabilities associated with it is something which we need to think. And the second thing is what is a shallow neural network? See, shallow neural network is nothing but a network where we have only one hidden layer associated, one or less. Okay, so what we are going to do is that, hey, we have a listing A. Okay, it's a 82 dim vector. Okay, it's a 82 dim vector, and we pass it to a neural network, a shallow neural network which has one hidden layer in it. And it's the work of this particular neural network is to convert this 82 dimension vector into a embedding which is of a fixed size. Let's say the fixed size is 128 dimension. You can take it 128 dimensions or a 256 dim vector, whatever you feel like. So let's convert this into a 128 dim vector. Okay, now similar could be done for this particular thing B. We have this shallow neural network, means it will be using the same shallow neural network, converting into a different 128 dimension vector. Okay, then what we do is that we calculate cosine similarity between them. Then what we can do is that this cosine similarity could be, we need to make sure that this cosine similarity is converted into a probability score, right? To convert into probability score, what is the best thing? Sigmoid. We apply sigmoid, we get a probability score, and we know that we are getting a probability score. So what loss function we can simply think of is binary cross entropy. So once we get this probability score out of this, we apply binary cross entropy to update the weight of this shallow neural network. And once the weights are updated, this one dimensional 128 dim vector would be automatically updated for A. And similarly, it would be done for B as well. So this is how our model will look like. But you can ask me that, hey, you showed me a different data, or how the whole stuff will work. Can you show me? Like, okay, I'll give you a small example of how everything will work. Okay, let's take this example, that user ID 1 clicked on A, B, C, D, E, and he booked F. Okay, now we will be using a sliding window approach here. Sliding window approach. Now what does this sliding window approach mean? Okay, now for every particular sample that the user clicked on, see, if we will start from let's say the sliding the window size is 1. So what does that mean? Let's start from B. If the user is seeing B, then we can show him A or we can show him C, right? If the user is seeing C, then we can show him B or we can show him D. If the user is seeing D, we can show him E or we can show him C, right? So this is a sliding window approach where the window size is 1. So we will be using uh, such approach to build our data set. So it means that when B will go, like here if you see, B will go, then C will go. Both of these gets into a 128 dim vector. 128 dim vector. Then cosine similarity happens. Then sigmoid goes. Then it goes for probability. Binary cross entropy is applied as a loss function, and eventually the model weights gets updated, and B and C are now closer to each other in the embedding space. Okay, but don't you think that we need to take care of this booking ID also? So to take care of this, we explicitly say that for B, when the user is seeing B, F should be also shown as a suggestion. When the user is seeing C, F should be shown as a suggestion. When the user is seeing D, F should be shown as a suggestion. When the user is seeing A, F should be shown as a suggestion. When the user is seeing E, F should be shown as a suggestion. And for them, the labels will be set as 1. But again, you can ask me this question that, okay, we have taken care of positive samples, but what would you do for negative samples? Because if we only give our models positive samples, then at the end, whatever you give to the model, whatever user listing you show to them, whatever listing you show, it will try to list all the recommendations, right? Then the model is a bad model. We don't want that. So for every positive sample, we can randomly send 5 to 10 negative samples. So for that, it means, what does it mean is that, for example, for listing B, we can say that, okay, listing G or H is not associated with it at all. It's not similar at all. So they should be far apart in the embedding space. They should be really far apart. Like if this is the embedding space, so if B is here, then D should be something here. They should be really, really far apart. And the labels could be simply set as 0. Okay. So here, this is the whole approach for building the model, a shallow neural network using a sliding window approach will help you build the whole system. And here we never take care of whether the user has even logged in or user has logged out, like he hasn't logged in the platform. Okay, now coming to the next part, that how are we going to evaluate our model? See, for this we have two things. One is offline evaluation, one is online evaluation. See, online evaluation is something which means that once the model is live, means you are using the platform and there is some recommendation system that is working to show you. So it means the model is live now. So how would you evaluate that model? And offline evaluation means that you have made the model. Now you want to check whether the model is good or a model is bad. Okay. So for online evaluation, there are generally two matrices in every recommendation system. One is a click-through rate. So let's say you are showing 5 recommendations, okay, and out of which the user is clicking 2. So the score would be 2 by 5. So total number of recommendations by number of clicked recommendations. Second could be session booking rate. See, what could happen is, whenever a user opens your website, okay, and he scrolled through but he did not find anything, okay, and he does it for 10 sessions, okay, in 10 sessions he booked only twice, okay, so the score would be 2 by 10, which is low, okay. So number of sessions that the user booked by total number of sessions, okay. And third and the final thing could be revenue. See, this is something which is very basic. If the revenue of your platform is going up, it means you are showing the correct the good recommendations to the user, okay. Offline evaluation. See, for offline evaluation, there are generally two matrices. First is recall at the rate k. Okay. Now, what does this recall at the rate k means? Recall at the rate k means number of recommendations relevant by total number of recommendations. See, whenever you are doing offline evaluation, you already are playing on old historical data. Okay, so you know what data you have. So for example, there was this user who already had this list of clicked IDs. Okay, let's say he clicked on A, B, C, D, E, and finally he booked F. Okay, you already have this data present with you, and then you made your model. And let's say your model says that I am showing him 5 particular things, that is B, D, H, I, J. These are the things which our model is recommending. Model recommends this. Model recommendation. So what would that mean? See, B and D are present here, right? The score would come, the recall score would come. Recall at the rate 5 would come. K means the number of recommendations that we are showing. So recall at the rate 5 would come 2 by 5. That is 0.4. Okay. Then comes the second matrix, which is quite important. That is NCDG. Normalized cumulative distributive gain. Sorry, the spelling is a bit wrong. The spelling is NDCG. That is normalized discounted cumulative gain. See, what does this mean is this helps you tell how good is your model in terms of ranking. So what does it mean is that, let's say our model is recommending 5 listings to the user. Let's say the user is currently viewing the listing that is G, and the model is recommending him A, B, C, D, E. Now ideally what should happen? That this particular listing which the user is finally going to book, it should be ranked at the top, means it should be on the first, right? This should ideally happen. So this normalized discounted cumulative gain helps you calculate that particular score on the historical data that we have. So we already know that what the user is going to book, right? So we are judging the model that whether the model is putting the booked listing on the top or not. Okay, now how do we do that? Okay, this is a very simple formula. NDCG at the rate is k is equal to DCG at the rate k by IDCG at the rate k. Now what does this mean? See, this DCG at the rate k is calculated by relevance of I by log 2 I plus 1, summation of all of them. I is equal to from whatever to whatever. I'll just tell you by giving an example that how do we calculate this score and how do we calculate this score. Okay. Let's say we had this data that a user was seeing this listing G and the recommendations that were showed to him are A, B, C, D, E. Okay. And this is rank 1, this is rank 2, this is rank 3, this is rank 4, this is rank 5. Okay. Now we know that that the user booked B. We have this data that user booked B, and even the user clicked before booking B, he clicked on A. Okay. Now what we do is that for booking and for clicking, we give some scores to them. Booking would have a score of 2. Booking relevance score is 2. Clicking score is 1. And ignoring for other bookings the score would be 0. Okay, so let's try to calculate. So this particular thing here would have a score of 2. This would have a score of 1 because the user clicked in our data. We have this data that the user clicked A and the user booked B. So this would have a score of 2. It would have a score of 1. This would have a score of 0. This would have a score of 0. This would have a score of 0. Okay. Now, how do we calculate this DCG? Okay. DCG at the rate k comes out to be summation of, so I'll rather than summation, I'll just tell you. So see, this was the formula, relevance of I. So what is the relevance score for this? It's 1. 1 by log of I plus 1, where I is the position. So it's at the position 1. So log of 1 plus 1 plus next comes B. What is the score for this? The score is 2. At what position it is? It's at second position. So 2 plus 1. Then comes relevance score for this. What is the score for this? 0. At what position it is? 3. Then comes fourth. This for D, what is the relevance score? 0. So 0 by log 4 plus 1. For the next also 0 by log 5 plus 1. So the score comes out to be 1 by 2 plus 2 by log 3 plus 0 plus 0 plus 0, which let's say roughly comes out to be 1.65. It is an approximate calculation. I'm not sure whether it will come out to be 1.65 or not. Okay. Then comes then the second thing which we need to calculate is IDCG. So what does this IDCG means? This means the idle case. See, in idle case, what should have happened? In idle case, it should have happened that B should have come on first. So the data in idle case, how the data should look like? B is 2. In idle case, what should be the idle case? Like B should be at the top of the rankings. Then should come A. Then comes the other 3 things, right? C, D, E. Right, this should be the ideal case, that B should be shown at the first at the top, then A should be shown second, then C, D, E. Right, this should be the ideal case. So for this 1, the relevance score is 2, it's 1, 0, 0, and it's at position 1, it's at position 2, 3, 4, 5. So again we calculate the score for this. How do we calculate the score? The same formula. Relevance of I by log 2 of I plus 1. So relevance score is 2, then the position would be log of 1 plus 1. Then comes 1 by log of 1 plus 2. Then comes 0 by log of 1 plus 3, and so on, plus 0 plus 0. The score would come out to be 1 plus 1 by log 3. So which will roughly come out to be 1.78 roughly. And NCDG at the rate k would be calculated using 1.65 by 1.78, which comes out to be roughly 0.9 something. So it means that our ranking quality is good, right? Now, what can we do if at the time of evaluation, our model is not good, or our evaluation comes out to be bad? Okay, there are few things which you can do. First thing is that I told you to generate negative samples, right? But at the time of generating random negative samples, what you can do is saying that, let's say some user is booking a room in Bangalore, which is 2 BHK. Okay, and he wants the amenities as Wi-Fi and some other stuff like car parking. This is what user wants, right? So for whenever we are generating negative samples, what we can do is that we can take samples which are close to this, like Bangalore 2 BHK, but they don't have the amenities available. Okay, so this can be generated as a negative sample. Or some other thing like Bangalore 1 BHK, but only has this Wi-Fi as a amenity. It does not have a car parking as an amenity. Such kind of samples could be used which are closer, which makes sense rather than just generating a random negative sample. Okay. Second thing which could be done is, see, I told you that the embedding dimension that we were using was 128 dim, right? Rather than 128 dim, we can extend it to a 256 dim vector, 256 or a 512 dim vector. These two simple solutions can help you make your model much better and increase the accuracy of the model. Okay. Now coming to the last part, that is serving. See, for serving, let's divide this, how the serving works. In serving, one thing is that you need to continuously train your model, because every other day new listing will come, right? So there will be a training pipeline. We are sure of that. There should be a training pipeline. And this is one thing. Second thing could be, okay, to the end users, we need to give top care recommendations, right? So there should be some serving pipeline. But you see, whenever you are training, what you are doing, you are just calculating the embeddings, right? So you need something which will take care of all that embeddings, right? So there should be some pipeline which is called indexing pipeline. Okay, how everything will look like, let's give one by one a deep dive. Training pipeline. Let's say new listing comes. You have this pipeline, which is your training pipeline. The fine tuning of your model happens. Model fine tuning. Okay, it gives you a final model. This is the simple work of your training pipeline. Okay, once your final model is developed, you need something uh, which will save that index. So basically you are generating a 128 dim vector, right? So you need something which will store that 128 dim vector for every particular listing, and somehow you need such a data structure which helps you calculate similarities between all the other embeddings as well, right? So then comes the indexing pipeline. So this is your indexing pipeline. Here comes the indexer. Here comes your index table. Here comes your listings. Okay, the work of this particular thing is to store your embeddings, in a way that they are easy to retrieve and fast to retrieve. This is the only work of your indexing pipeline. Now, how will this indexing pipeline work? Let me just give you. Once the serving pipeline comes, I'll tell you how this indexing pipeline works. Okay, so see, let's say user was seeing this query. This is the user. He is seeing some query. Let's say the query he is seeing is G. Okay, there should be some service which should be embedding fetching service. Now, what does this mean? See, he is just seeing a listing, right? Now, every listing, there is a 128 dim vector that is saved. Now, who is going to bring that? This embedding fetching service is going to bring that. So it goes there and tries to see whether for this particular listing, G, do I have the 128 dim vector associated to it or not? Yes, if it has, it will try to bring that particular 128 dimension vector with it. Okay, let's say if it doesn't have, then we will see what to do. But currently, let's see, it has a 128 dim vector associated, means G has a 128 dim vector associated to it. Now, the second thing would be approximate nearest neighbor. Okay, see what is going to happen. This is a 128 dim vector. Now, what I told you, it needs embeddings which are closer to it, right? So we need something which helps fetch the embeddings which are closer to this 128 dim vector, right? So for this, there is service called as approximate nearest neighbor. What it is going to use is, it uses a algorithm called as scan. Okay, what it does is, it tries to see what embeddings. See, embeddings would be in like a it's a 128 vector which can't be represented, right? But let's what I'm trying to showcase you is, let's say, it just showing by you an example of 2-dimension. Let's say if it would be a 2-dimensional. So if it is an embedding, then this approximate nearest neighbor service has to bring embeddings which are closer to it. So it will try to bring these embeddings to it. So this particular algorithm, which was developed by Google, will try to bring these particular embeddings near to this. And how it will going to, it has an index table, and it will try to just fetch the embeddings which are near to this. So I don't want to deep dive into this because again it will take a lot of time if I try to start teaching what is this algorithm. Once this approximate nearest neighbor service works, what will happen is that it will fetch, let's say, top 100 or let's say top 200 listings. Okay, top 200 listings it fetched which were near to this particular listing. Okay, the next task for this is a re-ranking service. re-ranking service. See this, what is this re-ranking service? Re-ranking service is nothing but a service which applies some business logics. So for example, let's say it in 200 listings, it's showing some listings which are like overpriced, like let's say it's costing you 50k per day. So the user would normally apply a filter that it wants to see listings which are like less than 20k. So re-ranking service is nothing but business logic that we apply over these 200 listings, that hey, exclude all the listings which are priced more than 15k, something like that. So this is re-ranking service. Once this service is applied, then we have the left recommendations that we finally show to the user. So this is how every single the whole similar listing service for vacation platforms gets built. Thank you.